Hello everyone, my name is Divyanshi Jain and the topic for my presentation is series solution of ordinary differential equation, and we'll also discuss some concepts like ordinary point and singular points. So we know that this is the general or standard form of writing a second order differential equation, that is p of x d square y by dx square plus q of x dy by dx plus r of x y is equals to 0. And by dividing the equation by p of x, we can also write it in this form: d square y by dx square plus q of x upon p of x dy by dx plus r of x upon p of x y is equals to 0. We also have certain equations like Bessel equation and Legendre equation, which are of these particular forms: x square d square y by dx square plus x dy by dx plus x square minus n square y is equals to 0. This is the standard form of writing Bessel equation. And 1 minus x square d square y by dx square minus 2x dy by dx plus n plus 1 y is equals to 0, which is the standard form of writing Legendre equation. Now let us discuss concepts like ordinary point and singular point. So what are ordinary point? A point x is equals to x0 is called ordinary point for equation 1. This is the equation 1. If p of x is not equals to 0 at x is equals to x naught. That means if we take any value of x, that is 1, 2, 3, 0, and we get p of x is not equals to 0, then x is equals to x naught will be called the ordinary point for that equation. Example, if we take the Legendre equation and we put x is equals to 0 in this. So on putting x is equals to 0 here, what are we gonna get? 1 minus 0, and that is equals to 1. So p of x is not equals to 0. So that means x0, that is x equals to 0, is an ordinary point for the Legendre equation. Now let us discuss singular point. And singular point is also divided into two types: regular singular point and irregular singular point. And there's one thing to be noted, that series solution exists in regular singular points only. Now, if p of x is equals to 0 at x is equals to x naught, so x naught is called the singular point. Example, in Bessel equation, now this was Bessel equation, x square d square y by dx square. In this, if we put 0 here, so p of x will be 0. So that means x is equals to 0 will be called the singular point in this case. And as we are getting p of x is equals to 0 in the Bessel equation. Now on further, if we move on to regular singular point, so what is regular singular point? A point x is equals to x naught is said to be a regular singular point of equation 1 if p of x is equals to 0 at x is equals to x naught, and it further fulfills these two conditions. That means it should be singular, that is the first condition, and the second and third condition is this: limit x tends to x naught, x minus x naught, q of x upon p of x should be a finite value, and limit x tends to x naught, x minus x naught whole square, r of x upon p of x should also be a finite value. In any of the case, if we are getting an infinite value, then it is a irregular singular point. Let us take an example: 2x square d square y by dx square minus x dy by dx plus 1 minus x square y is equals to 0. And the question given to us is that find x is equals to 0 is ordinary point or regular singular point. Now first we have to identify p of x, q of x and r of x. P of x over here is 2x square, q of x is minus x, and r of x is 1 minus x square. On putting x is equals to 0 here, what are we going to get? P of x we are going to get 0. So that means it is a singular point. It's not an ordinary point, it is a singular point. Now let us check whether it's a regular singular point or irregular singular point. Now to check that, we have to take these two conditions: q of x and p of x values we'll put, and we'll find out that on putting x naught is equals to 0, things will get cancelled out and we are going to get minus 1 by 2, which is a finite value. Now let us take the second condition. Here also we'll put the values of r of x and p of x, and on solving we are getting 1 by 2, which is also a finite value. In both the cases we are getting finite value. That means x is equals to 0. It is a regular singular point. Let us take one more example to make things more clear. if we have a question, show that x is equals to 0 and x is equals to minus 1 are singular point of this equation. Here also first we'll identify p of x, q of x and r of x. P of x is x square x plus 1, q of x is x square minus 1 and r of x is 2. On putting x is equals to 0, we'll divide it into two parts. One is when putting x is equals to 0 and the other is when putting x is equals to minus 1. On putting x is equals to 0, this whole will be turned into 0. That means it's a singular point. Let us check the other two conditions. On putting x, q of x upon p of x, we are putting q of x and p of x. X and x will be cancelled out, and after putting x is equals to 0 here, this whole denominator will change into 0, and dividing anything by 0 gives us infinity. So this is not a finite value. Let us check the other condition. X square and x square will be cancelled out. On putting x 0 here, we'll get 2 upon 1 which is equals to 2, which is a finite value. But if any of the value is infinite, that means it is a irregular singular point. So x is equals to 0 is irregular singular point. Let us check the other one. X is equals to minus 1. P of minus 1 is equals to 0. When we put p here minus 1, we'll get 0. That means it's a singular point. Now checking the other two condition, we are putting the values over here. X minus x naught, x minus x naught. So x naught over here is minus 1. So x minus minus 1, that will give us x plus 1. So x plus 1, and this is r of x upon p of x. This and this will be cancelled out. On putting x is tending to minus 1 over here, this will be 1 and this will be 0. So 0 is a finite value. Then checking the other condition, here also this and this will be cancelled out. Here we'll put x tends to 0, x tends to minus 1. So this will be 1 and this is 2 and this is 0. So this whole value will turn to 0, which is also a finite value. So the answer that we are getting is x is equals to 1 is a regular singular point. Thank you.